Hi, welcome to Pig Tuition's Maths Revision. This chapter will be on transformation for graphs, and there are several transformations to learn, and we'll quickly go through them. To start with, we have translation. Translation is basically shifting the graphs in the on the axis. So a simple example of a translation would be just to shift it to the left or right, up or down. So, for example, if we have a simple graph like this, quadratic graph, we can actually shift it, right? We can shift it to, let's say, to the right. Something like this. This would be a translation in the positive x-axis. So let's say when we try and translate a graph like this, right? We can label the original graph as fx, the later graph as, the translated graph as gx. So in the case of a gx, we can see that all x has been delayed. What is supposed to happen at x equals to 0, like here, is now happen at, let's say, x equals to, for example, 5, okay? So we know that g5 equals to f0, and gx therefore equals to fx minus 5, right? If it's the x from the g. So in a sense, we see that translation in the positive x-axis means that you replace x with x minus c, where c is the amount that you translate by. Okay? So here we see that it's basically here. It happens earlier. It happens earlier in terms of x, and x is translated in the negative x direction if it's a plus c. In our case, we minus the constant, so the graph happens later. Okay, so this is for the horizontal translation. It is a little bit counterintuitive because the plus means you are translating to the negative side and the minus means you're translating to the positive side. But just think about it in terms of whether if it's happening earlier or later, and this will help. In the case of a vertical translation, it's much more straightforward. If it's positive, it just goes up. If it's negative, it just goes down. So for example, a simple example will look like this, right? Let's say we have, it translates upwards. Then this is simply just a matter of y equals to fx plus c, where this is c. Okay? So in the case of scaling, we can also scale it horizontally or vertically. Horizontally is we stretch right or left. So using the same graph, actually, we can use the same graph for this as an example. We can maybe stretch it outwards. Okay, so we see that the entire graph is being stretched out like this. So this is a modification in terms of the x coordinates, and we can see that here how it's represented is that, let's say we have a point here that is 3, 10, and this point here is 6, 10. Okay, where of course we still have the fx and gx. So we say that g6 is equals to f3 in this case, in this example, and we can therefore write gx is equals to fx over 2, because in this case the x is referring to the input for the g. Okay, we see that although the graph becomes stretched outwards, the scaling factor on the function is actually 1 over 2. So this is basically a horizontally scaling. We see that when we replace x with cx, it means that a point previously at x equals to a, so in this example x equals to 3, now happens at cx equals to a, which means 2x equals to a. Okay, so 2x equals to a, then here you must sorry, here is 2x equals cx equals to a, where c is the unknown constant or scaling constant. So a is 3, right? And x is now 6. Then c must be half. Okay, so this means that the graph must be scaled to 1 over c. In this example, c is half, 1 over c is 2. So the graph is being scaled by a factor of 2 horizontally. Again, in the horizontal scaling, it is a little bit not very intuitive because you multiply the x by 2, but then the graph scaled by half. The graph squeezes half. I just remember it's like, it's a little bit counterintuitive. It's more like you're modifying the input. So yeah. In the case of the horizontal scaling, it is also known as the y-axis invariant. So sometimes it's called scaling, stretching with y-axis invariant. Okay, you'll notice that I use the word stretching and scaling quite interchangeably. So they're actually the same thing lah. Okay. So in the case of vertical, again, it's very straightforward. It's just a matter of graph getting multiplied in the y-axis by c when you multiply it by c. So here it might be easier to see a different graph. So for example, a graph that looks like this, a curve. If we scale it by 2, we scale it by 2 like this, we are simply just multiplying it, where gx equals to 2fx. So actually what we are doing here is just a matter of trying to describe the translated scaled graph, translated or scaled graph, using the original graph. And that can tell us how the graph can be changed to give us the changed graph. In the case of vertical, the last thing for scaling and stretching is, in the case of scaling vertically, it is also known as scaling with x-axis invariant. Then we move on to reflection. So reflection will be usually along the x or y axis. So these are quite generally quite straightforward. It's just a matter of a mirror image. So we are basically flipping all the x or flipping all the y. So if we are flipping along the x-axis, that means we are treating the x-axis as a mirror. So suppose we have this graph, we flip along the x-axis, we'll get this graph here. Okay, we'll get this graph here. We notice that because we are flipping around the x-axis, what changed is the y values. So the y values of the graph get flipped, and therefore the negative sign is outside here. In the case of reflection along the y-axis, then of course we treat y-axis as a mirror. So here the graph will look something like this. Yeah, something like this. Okay. So here what changed is the x-axis. And we see that therefore the negative sign is inside the function, modifying the input. All the x value flips their sign. And then we have modulus. Modulus means that all the positive values are retained while all the negative values are turned into positive values. So if the input produces a negative output, it is then changed into a positive output. One very simple way to show is just let's just do an example, okay? So suppose we have a graph that looks like this. We see that over here, for this range of x, we produce a negative output. If we want to draw a y equals to modulus fx graph, we will need to change all of that into a positive value. And that will give us a graph that looks like this. Yeah, something like this, yes. Okay. However, if now the modular sign is inside the function, that means we are modifying the input instead of the output. What it means is that all the input are changed into a positive value before being put into the function. So we are actually only seeing values from this side of the graph. Okay? In essence, when we have negative x, it will turn into positive x. And in this example here, the graph that we see will be, so for y equals to f modulus x, we'll see that the negative side behaves like the positive side. And you will get a graph that looks like this in the green line. Okay, so this is f modulus x. The blue line is modulus fx. And the original pink line is fx. So if you are confused, right, just think of this example. Usually it will help because these are more like simpler examples that can help you understand more difficult questions. Okay, for the case of reciprocal is probably the most difficult part of this transformations, because reciprocal has quite a few rules to remember. So there's like the points, because the output is being 1 over reciprocated. So all the points needs to be, all the output, which is the y, okay, all the y values will become 1 over the originals. That means 0, if it's, okay, let's just do a table. Okay, this is fx, this is 1 over fx. If originally is q, a constant, then 1 over fx becomes 1 over q. If this is 0, then 1 over fx becomes infinity. Okay? Then if this is infinity, 1 over fx becomes 0. This is basically the rules for changing all the points on the graph. Okay? If they are asymptotes, they behave in similar ways. So for example, for horizontal asymptote y equals to c, you see that it ends up being y equals to 1 over c. For oblique asymptote, which is a straight line, it becomes a horizontal asymptote that goes to 0. Why? Because the oblique asymptote goes to infinity eventually. And the horizontal asymptote therefore goes to 0. This goes to infinity eventually. Okay, maximum point become minimum point because when you do 1 over, what is the smallest becomes the largest. And increasing distance gradient therefore becomes decreasing distance, because we know that the maximum points, the bigger numbers become the smaller numbers. So as a very general example, that I'm going to just draw a general example that includes most of the, should be all of the rules that we just talked about. Okay. So suppose we have a asymptote at x equals to 0. And x equals to c, y equals to c, sorry. Yeah, and the graph look like this maybe. And there's an oblique, let's say there's an oblique asymptote. So oblique is just basically a straight line asymptote. Nothing rocket science about it. Where this is mx plus c. To avoid the constant being, yeah, we use k lah instead of c here for the horizontal asymptote. So here we notice that there is a maximum point here and the minimum point here, right? The asymptote would change into a 1 over c like this, 1 over k, sorry. Here, okay, let me redraw this part because it's too close to the previous axis. So let's say it looks like this. So here we notice that there is an intercept here, x-intercept. This point will become a new asymptote, vertical asymptote for the reciprocal graph. Okay. And now we should be able to draw the reciprocal graph. So to start with, we see that this is larger than k. This location here is larger than k. So when we reciprocate it, it will start from below 1 over k. This position, let's label it PQ, will be the minimum point P1 over Q. And because there is an asymptote here, we see that here it will go to asymptote as well, but it goes upwards because it's the positive. Okay? Notice how along all these paths so far, the gradient has always been the negative of each other between the original graph and the reciprocal graph. Okay? Now that we move past the asymptote, we see that the original graph is now in the negative region. So the reciprocal graph will continue out here. And it will cross the original asymptote. After crossing the original asymptote will become 0 for the reciprocated graph. After crossing the original asymptote, we see that in the positive x area, which is this area here, the original graph is positive. So that means this graph here would emerge positive. Okay? Also, notice that the original graph is all above y equals to k. So actually the reciprocated graph should all remain below y equals to 1 over k. So here this looks a bit too spiky. So let me redraw this part. And this point will correspond to this point as another maximum point here. Okay, doesn't really look like it, but the idea is there. And then it will tend to 0 as an asymptote because this direction it goes to infinity. So here it must go to 0. Okay, so this is an example of how to draw how to reciprocate the graph. I think this is the hardest part of this chapter. The rest of the stuff is generally easier than a reciprocal. Okay, and with that we move on to the last point of this short chapter. Is the order of transformations. So order of transformation is important when we are trying to transform the graph through multiple transformations. So it's usually it's like the Modulus or whichever way you learn the order of operation for those plus minus subtraction, plus minus multiplication and division. So if we do it the wrong order, it may have some issues. So one simple example is that if we have a graph like this, if we translate by 3, okay, let's say not just 3, let's just translate by we just translate up like this. You translate, then we scale it. Then we scale it so it becomes okay, like this. Then we scale it so it becomes like this. Okay, scale it so it becomes sharper, like scale it in the y-axis, okay, y direction. Scaling it with, this is also known as scaling it with x-axis invariant. Just a quick recap, okay? So it will look something like this if we were to translate first and then scale it. But if we were to scale it first and then translate, it will look like this, right? It will first, we'll scale it. First we'll scale it, it will look something like this. Then we translate and it will just be moved up. Like this. The first original graph, yeah. It's not snapping properly. But you get the point, right? You see that the final graph, this is when, the blue graph is when you scale in y-axis first, then translate by, let's say this is C, okay, by C. Whereas the pink graph is scale by C, then not scale by C, oh my god, translate by C. So we see that they will give us different answers and that's why it's important. So usually what we do is translation happens from inside the bracket before moving on to the outside. Okay, so a quick example will be, let's say we have a function and we perform a series of transformation on it. How will you move the graphs? This way. The first transformation we need to look at will be, from the inside, we look at the output, the input. The input is x. So the first one we look at is 3. So this, we first scale with respect to, we scale with 1/3 in the keeping y invariant. Okay, this is the first order of business. Then we translate everything in the negative x direction by 2. And this is the second thing that we do. Then moving on, between +5 and 4, we'll do 4 first because that's a multiplication. Here is a bit like Bodmer's. You do the multiplication first. And therefore, this 4 scales the graph in the y direction, keeping x-axis invariant by a factor of 4. So this is the third thing that we do. And finally, this is the fourth thing that we do, we +5 to everything. So we translate everything in the positive y direction by 4. Okay, with that, we have briefly covered the transformation of graphs. I hope you found this revision useful. See you next time.